applications. And this is joint work with Rihuan, who is also one of the participants of this workshop, as well as Carola-Bibiane. Okay, so UNets, I imagine almost everybody here present will know, is a standard approach to image-to-image tasks, such as segmentation or any inverse problem imaging, which can also be applied for 3D, for example. So the general concept is that we look at features in a neural network at different resolutions by using downsampling. But we also keep information by the use of skip connections in the form of concatenating channels from one resolution to a later upsample branch. So we have some layers, do downsampling, some layers again, downsampling, and so on. And then at some point, we will start upsampling again and recombine with features from the same resolution as before. And if we go to 3D or even very large images, the memory requirements will become prohibitive, which was, I think, actually the focus of the last year's code sprint, for example. So for many real-world problems, this is actually not possible to use at least full resolution 3D volumes with a UNet, for example. In this work, we try to introduce a drop-in replacement for these classic UNets, which work as well as in 2D as in 3D, that have a far lower memory footprint. And the technique we will be using is by the use of invertible networks. So first, just to remind you how important this UNet architecture is, I took a look at this Google Docs file, which I believe Max uploaded yesterday, with proposed algorithms one might implement during this workshop. And out of the 13 papers that were listed there, 5 of those actually use a UNet at some point in their own algorithm. So these are the 5 that I found there. Maybe I missed one, but this just goes to show that even if you go away from segmentation, where UNet is like the only thing people do in some form, even in deep learning for inverse problems, this UNet is a very important idea. Okay, so I already mentioned that invertible networks or invertible layers are one way of solving this memory constraint problem. So the big problem about high dimensional data is the fact that we need to store activations. And this is because for the backpropagation algorithm, which we need for calculating gradients with respect to weights, we need to store all of these activations in order to be able to apply the chain rule. Okay, so this is quite a full slide, I would say. So imagine we have a activation from an ingoing layer xi-1 and calculate the outgoing layer's activation xi via a nonlinear function phi I. So this is one layer or a sequence of layers. And we denote by theta I the layer's parameters. Then the loss will depend on the outgoing layer's activation. So we write, calligraphic L is some function of the outgoing layer's activation. And what we need then for first order optimization are the gradients of the loss with respect to the weights of this layer. And simply by employing the chain rule, we get that this derivative and its adjoint times the gradient of the loss with respect to the outgoing layer's activation can be used to calculate this required gradient. And what we see here, if we then just plug in the formula, is that in general, we need to know the ingoing layer's activation in order to be able to calculate this derivative, as well as the gradient of the loss with respect to the outgoing layer's activation. So what we need to know is this thing and this thing. And yeah, this one, basically we go from the last layer back to the first layer. We can throw the last iteration away, but these all need to be kept from the forward pass, basically. So this is why it's so memory expensive to do training on high dimensional data. One solution for this is using layers that are bijective, or one would say invertible. And if we have the outgoing layers activation still in memory, we can simply reconstruct by inverting xi in this case under the layer, such that xi minus 1 is equal to the inverse of our invertible layer applied to the outgoing layers activation. So if the whole network is invertible, then we can simply, going from the last layer back to the first layer, successively reconstruct and calculate gradients, so that the whole procedure is very, very memory efficient, because we don't need to store intermediate activations. We just need to keep actually one activation in memory at a time, plus some additional possible memory overhead for computing all of the intermediate values, such as, of course, calculating this, for example, also takes some memory. So, but in theory, at least, the memory requirement should be independent of the network's depth. And the question is now, of course, how can we actually construct these types of layers? So one thing we always need to keep in mind with invertible networks is that the dimensionality may not change throughout the network. And yeah, what's done in practice, for example, is that the whole network is made invertible somehow up to the last layer, maybe. So if you have a classification network, it's going to be invertible from the image to the final layers activations. So we have an invertible feature extractor, and then we have a small layer which maps to the classes, for example, in a classification case. So really the simplest way of constructing invertible layers is by the use of so-called additive coupling layers. And the idea is here to somehow split our activations into two parts. So we here denote this xi divided into two parts, ui and vi. And in convolutional networks, this splitting is usually done in channels. So if we have 10 channels, maybe ui is the first 5 channels and vi is the second portion. So 5 more channels, basically. Then we can define a forward mapping, phi I, which maps from the last layer's split activations to the next layer split activations by the following formula. So ui is vi minus 1, and vi is equal to ui minus 1 plus some function of vi minus 1. So f theta I here is some arbitrary function, which might be several convolutional layers plus ReLU activations, for example. But what's interesting here is that this formula is actually algebraically invertible. So just by pushing some terms around, we can see that if we have ui and vi available, we can simply calculate ui minus 1 and vi minus 1 by this inversion scheme. So other concepts for this can, for example, employ numerical inversion schemes, such as invertible residual networks by Jens Beermann and others, and Jens is also present. Okay, so the idea now is to apply this principle to UNets. And for this, we will develop a learnable up and down sampling operation, which is at the same time invertible. So this concept of invertible layers has already been applied to UNets, but only to the not to the up and down sampling portions, basically, such that it's only partially invertible in some sub-layers of the network, basically. And in this work, we want to develop an invertible UNet that's actually fully invertible from the first layer to the last layer. Okay, so maybe you guys had some question marks in your faces already, because downsampling, of course, is inherently non-invertible, since if we decrease the number of pixels somehow, the dimensionality is, of course, changed. And classical methods from image processing are, of course, bilinear interpolation or trilinear in the three-dimensional case, cubic interpolation, nearest neighbors methods, and especially popular in the machine learning literature, max pooling operations. So this somehow shows that we need to do something different. And the idea is now that if we increase the number of channels at the same time as we decrease the spatial dimensionality, that is the resolution in each channel, we can construct an invertible function. For example, if we have C layers, height h and width w, then what we could do, if we halve the spatial dimensionality in the height and the width, then we need to quadruple the number of channels. And in the following, we will mostly speak about invertible downsampling, because if we know how to invert downsampling, we automatically have a way of invertibly upsampling. And there, the roles of the channels and the spatial dimensionality is, of course, reversed. And from the literature, we basically also already know several types of methods which we can use for this. So here on the left, we see this famous test image that's used all the time in image processing. And in the middle, we can see the so-called squeeze or pixel shuffle transform. So each of those four images is actually supposed to be one channel. And the idea of this pixel shuffle is simply to take windows of 4 pixels, 2 by 2, and reorder the upper left one into this channel, the upper right one into this channel, and so on. So we actually have this subsampling operation realized with this pixel shuffle transform. Another very classical method, which comes from image processing, is for images the 2D hard transform, which transforms an image into 4 channels in this case, such that we get detail coefficients, which is basically approximation coefficients, which gives you basically what looks like a downsampled version of the image itself, and also edge information. So we have horizontal, vertical, and diagonal edge information. And this is actually an invertible transform. And it would be possible to build an invertible UNet with these. But in practice, at least for the pixel shuffle transform, this poses a bit of a problem. So if we were to apply the inverse of the pixel shuffle for later upsampling, then if we have diverse channel information, and it doesn't need to be very diverse in order to be able to see the problem, then we get artifacts, basically. So in this example, we have just 4 monochromatic channels to which we apply the inverse of the pixel shuffle transform, such that whereas before we reordered groups of 2 by 2 pixels into different channels, we now have to do the opposite, such that these checkerboard patterns will automatically appear. And this will basically always be the case unless essentially unless all of the channels look the same. So the network will have the choice to either produce very non-diverse features, which are then upsampled by inverse pixel shuffle, or we get artifacts. But in practice, usually both would probably happen. And another problem is if we then applied standard 3 by 3 kernels, we have a pattern whose period is not divisible by, or the 3 by 3 kernel is not divisible by this appearing pattern, so we automatically also get moiré patterns. So this is not what we want, basically. Yeah, the hard transform can be expected to work better, but what would be ideal is if we could learn a suitable invertible upsampling operation that is tailored to the feature extractor we learned in the layers before. And this is what we aim to do now. And actually, this can be done quite easily. So given some matrix theta that fulfills some dimensionality constraints, we can calculate a skew-symmetric matrix theta minus theta transposed. And by exponentiating this skew-symmetric matrix, what we get is an orthogonal matrix, where here in this case the rows are colored according to some scheme. And by applying some reordering operator, which just reorders each row of this matrix into convolutional kernels. In this case, we have a 4x4 matrix, which results in 4 kernels of size 2 by 2. This will produce an orthogonal downsampling operation, and meaning that for each, if we convolve by a stride of 2 in each direction, actually. So each group of 2 by 2 pixels within up to a certain pattern within the input image gets convolved with each one of those 4 kernels. And in each pixel, this means that each pixel of the output images, which are due to this stride, downsampled, this means that each pixel is the result of this image patch. This is the inner product of this image patch, which each one of those 4 kernels, meaning that this is the result of the convolution with this kernel, this is the result of the convolution with this kernel, and so on. And this is actually an orthogonal operation, meaning that the corresponding transpose convolution will very simply give us its inverse. And we can also express the invertible upsampling, in other words, with the corresponding transpose convolution, where the corresponding primal convolution is its inverse. So it's a very simple concept in practice. We just need to be able to somehow calculate the exponential matrix of this skew-symmetric matrix and be able to calculate all of the derivatives. So let's look at some examples. And this is the same example image we looked at before. And in the middle, you see a randomly initialized matrix theta that produces an invertible downsampling. And as you can see, this is able to produce some very diverse feature maps. So this is just randomly initialized, but we can, of course, also train this. And for the picture on the right, I just, by gradient descent, applied one norm minimization. And since any orthogonal transform is a 2 norm isometry, this simple 1 norm minimization will lead to sparsity. So this actually looks very, very much like the...
Sorry, quick question here.
Yeah, sure.
What was the training objective for this task here?
Just the 1 norm of this representation.
Oh, okay.
Okay.
So not just anything.
Yeah. So for sparsity, one could of course do like L1 over L2, but since the the L2 norm here is constant due to the use of orthogonal transforms, this will be basically pointless to divide by the L2 norm. So I just did the L1 norm minimization here. And the resulting representation actually looks very much like the hard transform, for example. And in terms of sparsity, they are almost exactly the same. So why does this work? The reason is that the matrix exponential map from the Lie algebra of skew-symmetric matrices, meaning matrices whose transpose is equal to minus the matrix itself, to the Lie group of special orthogonal matrices is surjective. So meaning that if we can produce, we can produce any special orthogonal matrix by exponentiating some skew-symmetric matrix, which we can simply produce by theta minus theta transpose. This is a full parametrization, even an over parametrization of the skew-symmetric matrices. And yeah, so this is just the special orthogonal matrices, but if we went to the orthogonal matrices, we can basically transform any special orthogonal matrix into an orthogonal matrix simply by switching some rows of the matrix, meaning that up to the order of channels that we get, we can basically produce any orthogonal matrix. And yeah, so the question is now, for example, how can we represent the Hart transform that we've seen previously? And this is given by this matrix, for example, whereas any symmetric matrix, for example, would yield the pixel shuffle operation. And this is, of course, just one way of producing orthogonal matrices. So other alternatives are Householder transformations, Givens rotations, or Cayley transforms. And really, it's up to you what you want to do and how easy it is to implement the necessary derivatives, for example. Here in this case, we decided for the matrix exponential because it was basically easy to implement. And this gives you theoretical guarantees by a very simple operation. So now let's look at the invertible UNet that can be constructed by help of this. So the fully invertible portion is contained in this box. And let's maybe look at this first before we look at what's outside of this box. So we're given some tensor representing a 256 by 256 image with 64 channels, to which we then apply additive coupling layers. So this is the nonlinear portion at this resolution. Then later, after we've applied some layers to this, we just split the channels. So for example, we can take half of the channels or 1/4 of the channels, which is what we usually did in the 3D case, because then we get a doubling of channels for each downsampling operation. And only in this case, half of the channels then get the learnable invertible downsampling operation applied to it, which means that the number of channels for this half gets quadrupled, while all of the spatial dimensions get halved. So we now get a 182 channel image with resolution 128 times 128. And this gets repeated. We have nonlinear activations, nonlinear functions, which are invertible. Then we split the channels, apply learnable invertible downsampling, which quadruples the number of channels from this half that we applied this to, and so on. And in the on the right side of the invertible UNet, we basically do the opposite. We apply learnable invertible upsampling, meaning that the number of channels gets less, whereas the spatial resolution increases. And then we apply, then we use the skip connections that we also implemented for the other half of the activations, the other half of the channels. And this concatenates the channels from the same resolution from the downsampling branch of the neural network. So this essentially looks like a classical UNet with some differences, I would say. So in the case of the classical UNet, we were able to concatenate all of the channels with this upsampled branch. But this is not possible if you want to make this fully invertible, because the overall dimensionality may not change at any point. And this is how you can construct basically a fully invertible UNet, which is contained in this box. So since any operation, any arrow basically here is invertible. So splitting channels, of course, is invertible. Concatenating channels is invertible if you know where to concatenate. And we have learnable invertible downsampling and upsampling, as well as these additive coupling layers, for example. Then if we now want to apply this to a practical problem, such as segmentation, what we can do is basically increase the number of channels going in from our data dimensions. In this case, if we have RGB images, we would have 3 channels. But if we want to have more channels, we can simply apply some transformation, for example, just a linear convolution, which is a good idea in this case because any linear operator is its own derivative, such that we don't need to store an additional activation. And then at the end, we can also, by applying, for example, a linear convolution, reduce the number of channels back to the number of channels that we need. For example, if we have 10 classes in segmentation, usually we represent this with 10 channels, meaning that we can reduce the number of channels from 64 to 10 in this case. And this is essentially how you can construct a very memory efficient version of the UNet for any task that you're doing right now with some UNet. Yeah, so this was recently released as a preprint. So this is actually the old version that you're seeing here. So like 3 days ago, we uploaded a new version, which contains additional experiments and further theory. And if you want to give this a try for your own experiments, you can just use our implementation, which we put on GitHub in PyTorch. So the code is not fully finished yet, but it's definitely in a workable state. So you can apply this to your own experiments if you want, but expect some changes in the future. Yeah, so at first we wanted to do this in TensorFlow, but I'll have to say that it was a waste of time because there seems to be some general problem with working with graphs in TensorFlow, which make this basically impossible. At least I couldn't finish it. But if anybody's interested in a half-functioning TensorFlow version and wants to repair it, write me an email. Okay, so what we cared about in the beginning was the memory consumption. So let's see whether this holds up to what the theory says, which is that we have a constant memory in the depth, meaning that we can make our network as deep as we want without having to store more activations. So what we constructed here was just an invertible UNet with 4 downsampling operations, and which we tried on 64 times 512 times 512 images, so rather large image data. And any sequence of additive coupling layers was parameterized by delta coupling layers, where we use the values 5, 10, 20, or 30. So this is a really, really large network then in the end for very large data. And we compare the memory efficient to the conventional backpropagation, which we can, of course, still calculate. So it's up to us whether we want to calculate gradients by conventional backpropagation or this invertible memory efficient backpropagation. And what we can see is, for example, let's look at the first row, is that while the conventional backpropagation uses 3.17 gigabytes maximum, so we recorded actually the peak memory consumption during calculating all of the gradients. The memory efficient backpropagation only uses 0.85 gigabytes, meaning that we only need around 1/4 of memory in order to train this network. Of course, by having to reconstruct activations, we have to do additional operations, meaning that our computation time necessarily has to increase. So while calculating all of the gradients, in this case, took 1.16 seconds for the conventional backpropagation. So this is averaged over 10 times. And the memory efficient version took 1.94 seconds, meaning that we have an increase of 67% in runtime, basically. But this is just the calculation of the gradients itself. So usually during training, this number would realistically be a bit lower because you have some constant overheads which do not depend on the backpropagation itself, such as calculating moments or loading the data. So in practice, this number would be a bit lower. Okay, if we then double the number of layers, so double the number of nonlinear layers in our network, we see that the conventional backpropagation behaves about as we would expect. So we don't have an exact doubling of the peak memory consumption, but almost. So we have 5.9 gigabytes in this case, 5.9090 gigabytes in this case, and just 1.09 gigabytes in the case of memory efficient backpropagation. So actually this, the theory that this will be independent of the depth doesn't hold in practice, but it's not quite clear why this is the case. So what we neglected in our analysis previously is that we also, of course, need to store weights, which might play a role here. And there's, of course, some stuff happening in the QDNN and CUDA backends, which are hidden from us in practice. But the ratio is even more decreased. So in this case, we only have 18.4%. And this pattern becomes more pronounced if we have larger networks. So in the case of the largest network, which is really huge, we only need 2.06 gigabytes for the memory efficient backpropagation, whereas the conventional backpropagation will use more than 16 gigabytes. So this doesn't fit most commercially available consumer graphic cards even anymore. So in this case, the ratio was even 12.2%. So you can basically fit much, much larger networks into your graphics card. So these roughly 2 gigabytes will fit in any consumer grade graphics card. But we pay somewhat of a price for this since the runtime increases apparently with the depth of the network. So in practice, expect some slower runtimes, but a large increase in manageable network sizes. So what's of course now interesting is whether this holds up for experiments. And for a learned post-processing task, I used this FUM-CT phantoms, which I believe was made by Daniel Pelt, who is maybe also present right now, or he was there yesterday at least. And what we did is create these artificial foam phantoms of unsampled parallel beam CT data, where we actually have a slanted and perturbed axis, such that really the 3D case is what we need in order to be able to denoise low quality filtered back projection reconstruction. So as you can see, so this was all done in 3D. The reconstruction by filter back projection is really abysmal because of the large amount of noise and the low amount of angles in this case. And we applied then an invertible UNet at a resolution of 256 times 256 times 256 in order to denoise this low quality reconstruction by filter back projection. And as we can see, if we compare this to a standard 3D UNet and then apply our 3D invertible UNet, we get generally much higher structural similarity indices and PSNRs. So scales here denotes the number of downsampling operations +1, basically. So 4 scales means we have 3 downsampling operations, and 8 means that we have 7 downsampling operations. And the channel blow-up means the number of channels that the data was increased to in order to then perform the fully invertible training scheme to this. So what we can see is that increasing the number of scales actually helps our network, and increasing the number of channels helps our network. And for the largest network that we used, where we have 8 scales and a channel blow-up of 16, the standard 3D unit wasn't even able to fit into memory anymore, whereas our network got additional gains in performance compared to the previous iterations. And we assume that this gain in performance is, at least in parts, also down to how the network itself is constructed. So we actually initialized this such that the whole pipeline is initialized as the identity transform, due to basically a clever initialization of layers. So this means that an initialization, every layer sees a part of the input up to some orthogonal transformation. So since the whole pipeline is supposed to be rather close to the identity, so remember this is just supposed to change the input to some degree, we assume that this really, at least in this application, gives you an advantage for this post-processing task. And if we then look at some examples from the best performing 3D unit and the best performing 3D invertible unit, you can actually see with your own eye that the reconstruction is much better. So the standard UNet has some problems, for example, seeing this hole right here, because it's basically hidden under noise. And it also has problems of discerning these 2 neighboring holes, whereas our fully invertible UNet has no problems telling these apart. So as a second experiment, we looked at a 3D segmentation task. This was on the brain tumor segmentation 2018 challenge, where we have volumes of size 160 times 192 times 128. And we have 4 input channels, which stands for several MRI modalities that we measured. And here we compare the biggest UNet that we were able to fit, where we also have 4 downsampling operations, with several fully invertible units, where the number indicates the channel blow-up, meaning the number of channels that we increase the inputs images or the input volumes to. In the case of the standard unit, this were 24 channels, by the way. So what we can see is that on average, increasing the number of channels beyond what's possible with a standard 3D unit, we get a somewhat pronounced increase in performance, both in terms of dice score as well as sensitivity. So from 0.833, we get a boost up to 0.85. So what you can see is that actually going beyond what's possible with standard training procedures gives you a gain in performance. As a third experiment, we were also looking at normalizing flows. And this is something that can actually only be done with fully invertible networks. And the background for this is the so-called change of variables theorem. So if we have some random variable z with known probability density function q, usually a standard normal distribution, then for any local diffeomorphism f, it holds that the random variable created by f to the -1 of z follows the following distribution, which we can, if we can actually calculate this specific, we can calculate this basically. This means that for some point x, the probability density of x can be expressed with the following formula, meaning that for some point, some image, for example, we can calculate its likelihood under this model. And this gives us the possibility of training a generative model that can be trained by applying the maximum likelihood principle, meaning that if we are given training data, we just plug the xn, denoting the different instances of our image data into the formula, and then try to maximize the likelihood or minimize the negative log likelihood. Then we get a maximum likelihood estimator of the training data under the network. And by then inverting, we can actually create data, artificial data, from randomly chosen points. So we have a normal distribution, we pick some point, then run it through the inverse of this network, and we get an artificial image, just like in the case of GANs, for example, which on the other hand doesn't give you the possibility of estimating likelihoods in this case. And this is really something you can only do with fully invertible networks. So at the first try, we applied this to Cypher 10. And as you can see, on the left, we have the real images. On the right, you have some generated images. And these look, not perfect, I would say. But one has to say that even for the best normalizing flows on Cypher 10, the images don't look that much better, to be honest. So this really shines when you have more structured images. So for example, in the case of Celeb A, which are much bigger images, you get also much nicer pictures. But for applications, this is really useful if you want to, for example, estimate the likelihood of a point. And for this first try, we got a test negative log likelihood of 3.6 bits per dimension, which is usually the measure we use to compare normalizing flows. And the most comparable method on this data set yielded 3.49 bits per dimension. So we were somewhat close, I would say, but still not better. But in the future, what we want to do is look at this a bit more closely. I bet there's a lot of engineering involved, and maybe we can scale this up to larger images, which is where we expect the fully invertible UNet actually to shine. Because if it works for any image data, why shouldn't a UNet structure work for normalizing flows, basically? Okay, and with this, I would like to close and thank you, and I would be open to questions.